Good day, chaps. So welcome back to our chat on the Contentious. This time looking at the Contentious 1 that came about in the late 50s as part of Project Prodigal, a huge overlapping project aimed at the future generation of British vehicles. And one has to give kudos straight away to whoever came up with the names for both aspects, as let's be honest, he's not wrong. Prodigal covered a huge variety of vehicles, from jumping jeeps, trucks that could turn into helicopters, or supply vehicles that were half logistics, half flying swept-wing jets. The tank and wheeled vehicles were somewhat offset, although under the same umbrella, as both had to be at least air-portable and deployed from the back of a Blackburn Beverley aircraft mid-flight. Neither project is directly connected to the previous Contentious in the way of successorship, and neither have the title FV4401. But lessons learnt from that vehicle were applied. For example, the one-man crew was deemed inferior, and so the new vehicles had a minimum of 2 crew. External weapons were also discarded. However, low weight and high protection were still required. The second thing that might surprise folks is that while it's often touted as Britain's S-Tank, it wasn't, and would have been a turreted vehicle, albeit with limited traverse. However, there is a connection to the S-Tank along the way. So the team had to design a tank that would fit into the aircraft hull, pack heavy firepower and armour, and be rapidly deployable. As a result of this, they set out to build a low-profile tank that used adjustable suspension, but also had a high rate of fire and be very accurate with the lowest acquisition times. Work began in earnest over the next 7 years, and was split into several parts, each tested in different locations: the armour, the airdrop aspects, the gun and fire control elements, and the suspension parts. So we'll begin with the armour. In order for the vehicle to have the armour able to stop the threats of the time, the team went for a combination of armour systems, as conventional steel armour, no matter the angle or thickness, was proving relatively useless against the new anti-tank guided missile and heat threat, and did little but add large amounts of weight to the hull. They knew that angling the armour was needed, and despite the idea the British were lacking in this aspect, they were well aware of the process, but also of its inherent downsides, until tanks like Centurion, the angling aspect was less pronounced, although it is there if one looks. However, they were also at the same time undergoing a lot of evaluation on spaced armour arrays, with work done by Downey and Harvey at Chertsey, which would lead to the Chobham-style armours, and the work done on Contentious would also somewhat feed into that. However, they also felt that the space between these plates was very wasteful, and that any filler material could play a dual role, and thus using the vehicle's fuel at the front would not only give it superb protection against shaped charge attacks, but also provide the vehicle with a very large operating radius. Now, while it might sound quite crazy to use fuelless armour, it does in fact work. As with shaped charge attacks, the penetration is inversely proportional to the square root of the density of the target material. So the strength of the material, while not irrelevant, is overruled by density considerations to a large extent. For more on this, go and check out our other video on how much cheese does a mouse need. Thus, they chose to use diesel fuel as their low density material, as pound for pound it was more effective than steel, and had a secondary benefit that the tank needed it. However, criteria was applied to this, namely, that at no time, with any foreseeable anti-tank attack, shall the fuel compartment be so penetrated as to allow the fuel to enter the crew compartment, that the compartment must provide multi-shot protection, and penetration by a single round must not cause any loss of firepower or mobility, and finally, that the compartment should, if at all, be equally immune to attack whether full or empty. They began to test many ideas out. By creating the fuel tank with the correct sloping, any solid shot that perforated the first outside skin would tumble. Thus, if it made it through the space, the round would strike the backing armour with greatly decreased efficiency. But this led to 2 primary problems. The first was how to seal the fuel tank once it had been perforated to prevent all the fuel pouring out, and 2, how to stop hydrostatic shock. The former they never quite got to work well enough. Materials such as glass-reinforced plastic foams prevented some leakage, but not all of it. However, the bigger issue was some hydraulic transient effects, or water hammer. In the test, they noted that although the rear plate was able to stop both the 90mm and 100mm heat rounds and 20-pounder shot, the unfortunate downside was that the liquid tank would rip itself apart violently. And having a tank explode into pieces when hit is not a desirable engineering trait. This was due to the pressure surge, the fluid altering direction and expanding as the round or jet penetrated the material. And as you probably know, fluids cannot easily be compressed. Thus, as a general rule, the volume doesn't change. This fluid displaced has to go somewhere. It can't evacuate the hole just yet, and in the case of the expanding jet entering the armour, the pressure from that far exceeds the water. And so once the water pressure hits the steel walls, it has a few side effects, from simply splitting at the welds or cracking the plate, to ripping the big container into huge chunks. Various options were tried. One example used 3,000 rubber balls filled with air to line the sides, as a sort of crumple zone. However, this reduced the internal volume by 18%, but also didn't work. The tank filled with water still exploded, quite spectacularly. The next attempt used a rubber-zote mesh weave on both the sides and on internal strips. This took up less volume at 11%, although unfortunately it still caused splits, although smaller. However, none of the rounds were able to perforate the back plate, and just copper deposit was left or mild dents. The team felt that they had basically got the right ideas, but would need further work and investigation from the materials department. They did try replacing the mild steel used on the previous tests with hardened steel, using mock-ups mounted to old Churchill tanks. These proved to be more resistant, but also more problematic in how to fasten the plates, as hardened steel is a bit of a sod to weld, and leads to weaker joints, which of course still led to split seams, although the armour itself didn't shatter. Yet in one case the front of the glacis plate did explode out 20 foot from the test tank. They then tried using cast armour steel tanks. These proved to be a bit more effective than the welded tanks, as there's no obvious seams. Some bulges formed and some cracked, but didn't explode. Although these were only rough casts and not to the extent that would be used or refined in any finished version. On top of this, linter foam sheets were added, both inside and out, to act as a self-sealing fuel tank. This more or less worked and was marked down for further study. The next bit was how to protect the upper aspects of the armour. While the fluid would stop the inner armour being perforated at its greatest width, a shot to the upper angles had less material to travel through. Here they turned to the work of men like Harvey and Downey, and went through a few possible ideas in special spaced and ribbed armours. Ribbed armour is just as it sounds, and you might have seen it on vehicles like the S-Tank. Rather than one solid monoblock of steel, you have a series of raised sections of armour, which any round has to chew through, constantly losing energy each time it strikes a new section. And while it's heavy, it's still 50% lighter or more than the conventional steels of the same area and volume. And the UK had been dabbling with this for a while and had some good grasp on it. This came in a few varieties, mostly ribbed or slatted armour, and it was tested against the 20-pounder APDS from Centurion and from the Conqueror using both 120mm APDS L15A1 and the American T11-6E6 armour-piercing ballistic capped round from just 120 yards away, and both of these were fired at the applique fitted over the fuel tank. The ribbed armour was 50mm thick ribs, 12 inches high, at 60 degrees, while the slatted front armour was 40mm slats angled down at 70 degrees. The results from close range were mixed. The 20-pounder struggled, and even the outside layers with some damage and some shatters. None of the inner armour was holed. The L15, normally able to perforate around 390mm at 2 kilometres, was able to perforate the inner 40mm steel plate on both occasions, albeit fired from just 120 yards away, or in tank terms, point blank. The American round passed through the outer armour, but failed on the inner plate. The louver or slatted armour was also tested in a few configurations. After this, they filled the gaps in the louvers with concrete. These later tests proved very satisfactory, stopping or resisting the 120mm round, 20-pounder and shape charge attacks at point blank, and was particularly effective versus the shape charge, stopping all 6 attacks. The armour worked, although some fuel was still being lost, usually down to a pint or so. Overall, the armour weighed a lot less than the current main battle tanks and was far more resistant, and feedback from this was then sent down to the guys at Chobham working on their armour. So moving on, let's have a look at a running gear of this, as it's also very unique. In order for the vehicle to fit inside the Beverley aircraft, the team knew that a conventional tank would not fit, and certainly not survive being tossed out the back mid-flight, yet still have the armour needed. Thus she would need a low profile. To do this, the team designed an adjustable suspension system that would allow the tank to raise or lower its suspension and tilt the gun in depression or elevation. Now, this is nothing new today, but back then this was pretty revolutionary. In fact, it's worth noting that during the early stages, the late great Richard Gorkowitz was involved with this project and would frequently correspond to the Swedish tank designer Sven Berg, a close family friend, and swap ideas or suggestions. The question remains, who came up with the idea first? Several mock-ups were made. Some were used for airdrops, which we'll cover later on, but the core of the hull was a bit of a mishmash job. The body of the test bed was actually from a charioteer, although it's often recorded as a comet. However, in my archive delvings I came across 2 documents. The first, and then the older of the 2, written by Mr. N.P. Barton, notes that the hull itself was reclaimed from a charioteer, while later on a transcript of the same document commonly circulated changes this to comet. The front eider and return rollers are no doubt from the comet. Meanwhile, the road wheels are not taken from a comet, as it's touted again, but from the FV300 hull, which was made, and which was also the case for the previous FV4401 mock-up model. The test rig used a hydraulic system to tilt the vehicle up and down, which allowed the gun to raise and depress, but meant that the actual breech remained aligned with the proposed autoloader system, and therefore the turret could be kept to a low profile. The gun's traverse was initially 20 degrees left and right, although 30 degrees seems to pop up a fair bit in other text, and the elevation was recorded as plus 20 and minus 10 or minus 12 degrees, with sources varying. The original hull never had a working gun fitted initially, and just a tube added, and tests were done in Scotland with a Centurion with its traverse and elevation limited for testing out the angles needed. Later on, a large blocky system was added with a new sight system developed by CSIRA, or the British Scientific Instruments Research Association, using pulsed light in a similar method to the experimental OPTAR systems in the United States. This basically fired out a high pulse of light and then detected the return flash and could work out the range. However, it's not a laser system, which would come about in tank technology some years later. These early tests were very effective, out to around 2,000 meters, giving an acquisition time of just 2 seconds. This, however, was also very heavily dependent on the weather, with fog and rain drastically cutting its effectiveness. The vehicle also had the very first type of MRS, or muzzle reference system, although then called a muzzle mirror system, and work from this would go on to the Chieftain. The weapon fitted initially was a 20-pounder barrel and breech, and the theoretical acquisition time for the whole setup was 2 seconds, with a rate of fire of 12 to 16 rounds per minute. Interestingly enough, the block mounting the whole system ended up causing quite a few problems to the team in traverse angles due to the anti-roll system, and so a large section was shaved off one side, which is still visible today. Another noticeable difference is that the gun has changed, and the one in the museum now supports a 105mm gun, although whether this was done by Bovington or earlier remains unanswered. Well guys, that's enough for part 2. In part 3 we're going to look at the airdropping test beds, as these too often get some confusion about them, as well as Contentious 2, which also remains today. If you like this or want to know more, please do give it a subscribe or hit that notification button, and hopefully we can catch back up. But until next time, toodle pip.